Sometimes we take it for granted that we are all living on the crusty surface of a planet, divided into tectonic plates, which float atop a whirling mass of molten rock. By understanding the strength of these tectonic plates means that we can better understand events such as volcanic eruptions and earthquakes. However, a difference in estimates of plate strength from lab experiments and real-world observations has puzzled scientists. Until now. I'm Michael Wheeler, and I spoke to Lars Henson from Oxford University.
The Earth's surface is split into a bunch of different tectonic plates. And over geologic time, they move around and they bump into each other. And that creates all kind of phenomena that we're familiar with, like volcanoes and earthquakes. We're trying to figure out what the fundamental controls are on how these plates move around and to get an estimate of how strong one of these plates are. What do you need to do to get it to break? So we're talking about processes that are deep in the Earth, tens of kilometers thick, or it might be hundreds of kilometers thick. The rocks that are involved, they're subject to pretty extreme temperatures and pressures.
So pretty tricky to try and replicate those conditions in a lab.
That's right. And that's the big difficulty. So there have been people working on this for quite a few decades now. And there's very sophisticated instruments out there, these big apparatus that apply these huge forces to small rock samples and get them to great pressures and high temperatures.
I'm just imagining these large apparatuses as being similar to car crushers. How accurate would my imagination be in that case?
Right. So I don't think that's a bad analogy. A lot of these are sort of hydraulically driven. And one problem that we've had is that a lot of the experiments that have been done have not agreed with each other very well.
What's the novel aspect to what you've done?
We're working with a more modern technique that's producing pretty exciting data. That technique is having the press based at a synchrotron, and a synchrotron is a very intense X-ray source, and so you can use those X-rays to actually see through this large press with the sample feeling really incredible pressures, and you have an image of it, a live image, and you can see it right there and see exactly what it's doing.
In real time?
In real time. Really incredible. And on top of that, we're using a technique referred to as instrumented nanoindentation. And in this technique, you would take a very small diamond stylus, and it may be millionths of a meter, and you take that and press it into one crystal of the material that you're interested in. And you can generate really large pressures because you're pushing on such a tiny area.
Why do you choose the crystal of the material and not some other part of the material?
So these rocks are really built out of lots of crystals. One thing we want to do is isolate the properties of just the crystal by itself.
Yeah.
Right? So our goal was then to measure the strength of this key crystal of the mineral olivine, which is what we think is really important in making up a lot of a plate. And what we ended up finding is that rock made out of really big crystals would overall be really, really weak. But a rock made out of really, really tiny crystals would overall be strong. So we went back and looked at all these previous data sets and plotted the measured strength versus the size of the crystals. And what we realized is there's this really nice relationship. So it turns out all this variability was because people were using crystals of different sizes in their samples. On top of that, all the previous experiments were overestimating the strength because they were, in general, working on really, really small crystals in their samples. And the size of the crystals in the Earth are actually really, really large.
How do we know what the average crystal size of these rocks would be?
Okay, excellent question. So certain volcanoes have sitting in the lavas xenoliths, which means alien rock. And they have a composition and a crystal size that is representative of the deeper parts of the plate right at that location.
And by knowing about the strength of these rocks from your experiments on these crystals, does that tell us anything about when earthquakes might happen?
There are certainly links to the earthquake process. So these faults are sitting there. They have a lot of stress building up, and at some point, they rupture. That rate of evolution of the stresses on that fault is going to be controlled in some manner by the size of the crystals right in that critical region.
So scientists have cracked the case on tectonic plate strength. That was Lars Henson, and his work was published in Science Advances.